that it's going to be too dense. Part of my talk will be only briefly fleshed. That is recent studies that we did in the impurity limit on repulsive Fermi polarons. All the things I'm going to tell you about are done in the lab of Giacomo, with which I have a very fruitful and nice collaboration over the last years. And what I want to focus more on is a more recent study on balanced systems, on balanced mixtures of lithium-6 atoms in two spin states, and where we investigated the real-time dynamics of the gas in the regime of strong repulsive interactions. Good, just to give you a kind of brief motivation why we like to study repulsive Fermi gases. I think the original motivation is connected with the so-called Stoner's model for itinerant ferromagnetism that is something like the aims to explain the ferromagnetic phenomena of whatever fermionic particle that is not pinned into a lattice, but rather it's delocalized and therefore itinerant. And the Stoner model itself, it's a very simple model that is a kind of mean field model that is considering just a binary mixture of up and down fermions, characterized by a certain density, a certain Kf, and a certain Fermi energy. And in contrast with the Coulomb interaction, Stoner considered a screen Coulomb interaction that in the kind of minimal framework can be approximated with a contact-like interaction. Therefore, a repulsive Fermi gas of ultracold atoms appear like, let's say, an optimum framework for investigating for the quantum simulation of this kind of minimal model. Yeah? Essentially, the minimal model of Stoner predicts that essentially if you crank up the repulsive interaction up to sufficiently strong values, you will undergo from a paramagnetic to partially ferromagnetic to a fully ferromagnetic state. And let's say the thing that also Giacomo was showing in this picture closely resembles what Patricia was discussing about bosons, bosonic mixtures. The only problem is that we are dealing with fermions, and so instead of having a competition between interspecies and intraspecies scattering lengths, this time you will have a competition between interspecies scattering lengths and Fermi pressures. And if it's quite easy and straightforward to see that, let's say, the mean field model will predict these phase transitions to occur at relatively strong coupling. That makes, let's say, on the one hand, the Stoner model itself highly questionable. On the other hand, since it's a strong coupling phenomenon, possibly quite interesting. However, there is a kind of subtle thing happening, that is that the ground state of the Stoner model is not ferromagnetic at all. And this comes from the fact that the contact interaction, rather than a long-range interaction, can be repulsive only if a bound state, a two-body bound state exists. So hard-sphere interaction potential, you can crank up the scattering length with the radius of the sphere, but let's say if you just pretend to bring the radius of the sphere to 0, also the scattering length will be 0. This means that, as also Giacomo was anticipating in his talk, the physics we are going to look at happens on an excited upper branch of the many-body system. This, let's say, kind of sketch from Prikupenko and Casten nicely shows this. That is intrinsically unstable towards decay, towards the true ground state. That is the BC-BCS crossover where we do Josephson dynamics or crossover superfluids. So this makes things more difficult on the one hand, and even more interesting on the other, at least from my perspective, because on the one hand, neglecting pairing, various theories beyond the main field, for instance, quantum Monte Carlo or more sophisticated theories beyond the Stoner model, indeed predict that the repulsive Fermi gas can undergo a ferromagnetic instability for sufficiently strong repulsion. On the other hand, if theories do not neglect pairing into the problem, then the situation becomes much more difficult in the sense that many theoretical works show that either pairing is going to be faster than ferromagnetic instability, or even that the repulsive branch of the many-body system is going to be ill-defined. And from the experimental side, there was quite a bit of work, something like almost 10 years ago, pioneered by the group of Wolfgang Ketterle, that investigated these dynamics of repulsive fermions, rapidly brought close to a Feshbach resonance by means of a magnetic field sweep. And despite a first positive indirect indication that would have pointed to a ferromagnetic phase transition, the same group a few years later kind of ruled out, let's say, the possibility that the repulsive Fermi gas could ever turn ferromagnetic. And their conclusion was that an ultracold gas with short-range repulsive interactions remains in the paramagnetic phase. And let's say the widely used Stoner model cannot be realized in nature, since the neglected competition with pairing is crucial. Yeah? On the other hand, as Giacomo was showing you, in recent experiments done in our group, we could demonstrate that indeed if you overcome in an artificial way, let's say, the problem of pairing by artificially creating the ferromagnetic ground state by means of this configuration, the spin dipole frequency showed a softening and then a sudden jump that is strongly suggesting that ferromagnetic instability is present into the system. And let's say that would be my only slide on the N+1 part of my talk. Also, we performed radiofrequency spectroscopy in the impurity limit, where we have a few spin-down impurities embedded into a spin-up Fermi gas of lithium-6 atoms. And in contrast with the theoretical expectations for the mass-balanced broad resonance case scenario, we found out that indeed repulsive Fermi polarons, that are the building block of the repulsive Fermi liquid, indeed remain well-defined up to very, very strong interactions. And in addition, we could verify that the energy of this repulsive polaron for a critical value exceeds the Fermi energy of the bath, which in the language of, let's say, an electron gas where you can really flip the spin, it would signify that the ferromagnetic phase in the impurity limit is energetically possible. Yeah? So our questions and our motivations are the following, essentially, that we want to address the following questions. So can a strongly repulsive Fermi gas exist, at least temporarily, also in the balance case? Can short-range repulsion alone establish some kind of ferromagnetic correlations into the system? And if yes, how pairing and magnetism compete and coexist within the many-body system? So our strategy is slightly different from the one employed by Wolfgang Ketterle's group in the past, and it is based not on a fast whip of the magnetic field, but rather on a coherent population transfer that exploits the nice feature of lithium-6 atom that has three internal, the three lowest internal spin states that present two off-centered broad Feshbach resonances that enable us to prepare a weakly repulsive mixture of, let's say, 1 and 2 state atoms. And by means of a radio frequency field, we can couple and quickly transfer the state 2 atoms in the state 3 atoms, and therefore create from a weakly repulsive mixture a strongly repulsive one. Yeah? And you can think to the initial system as created by a bath, kind of, let's say, a Fermi gas of state 1 atoms at T over Tf of order 0.1, Fermi energies and Fermi times of order of 6 kilohertz and 25 microseconds respectively. And then we prepare the system at equilibrium in the weakly interacting state 2. And then, by means of a radiofrequency pulse, we want to populate the repulsive branch of the 1,3 mixture. And in order to do this, what we do first is, okay, we calibrate our magnetic field, fine. And then, in the presence of the state 2 atoms, we perform a 2 to 3 radiofrequency spectroscopy. These are the red line. This is the red line that enables to pinpoint in the spectral response both the location of the upper branch of the many-body system as well as the lower branch that is associated with the association of dimers in the BEC limit. Yeah. Sorry. Yes. So let's say the preparation of our strongly interacting mixture then is done by means of a radiofrequency pulse that is blue shifted relative to the Baeyer atom transition. So we populate the repulsive branch. The advantages relative to a fast magnetic field sweep are the following: that the process is very fast and efficient because we can have a sort of coherent population transfer in times that are smaller than, shorter than 10 Fermi times, with relatively high transfer efficiencies, even at very large coupling. What is very important to stress is that our method is spectrally selective in the sense that only the repulsive branch is populated with this method and no pairs are created during the quench. So other things that I would like to stress is that no many-body dynamics is established during the pump pulse itself. And on top of that, the pump spectroscopy that we do in order to pinpoint this delta plus 0 at different KFA values automatically enable us to understand if the repulsive gas remains well defined or not. Until we see a coherent peak shifted at positive energies, we know that the repulsive Fermi liquid is well defined. Okay, this was about the preparation. Then I come to the experiment that allows us to monitor the many-body dynamics of the repulsive Fermi liquid. And the protocol is very similar to what is done in pump probe experiment in the solid state. That is, we first apply a pump pulse plus an optical blast that remains removes very quickly eventual leftover atoms in the 2 state. Then we wait for a variable hold time such that the many-body system evolves, goes somewhere, yeah, and then we make after a variable hold time a probe RF spectroscopy pulse from the 3 state to the 2 state that is empty after the blast, and we look at what happens. So in the probe RF spectra, we see different features that, let's say, enable us to monitor both pairing and interaction shifts. Yeah? So here it's an example at very strong coupling, so that, let's say, the molecule feature in the spectral response is very well visible. Here it's at moderate interactions close to the strong coupling regime at KFA of order 0.9, and it focuses only on the repulsive peak. Yeah? So from this kind of spectra, the height of the coherent peak is directly linked to the surviving population of atoms in the state 3 that remained in the upper branch. If they became molecules, they would never respond at this frequency detuning. And on the other hand, interaction shifts the center of the repulsive peak, the frequency detuning of the repulsive peak, this delta plus T, so defined, provides us information about the column integrated interaction experienced by the atoms. In particular, let's say, if there is no peak, it means that I will have all the repulsive Fermi liquid converted into molecules, so there are no unbound fermions left over. On the other hand, if the shift goes to 0, this is related somehow to the pair correlation function at short distance. It means that presumably the system undergoes kind of phase separation and domain formation. This was the idea. So here I just show a few examples of, let's say, evolution of, yeah? Let's say we are dealing with contact interaction. So if let's say the system is not shifted, does not feel any interaction shift, it means that nearby at least the fermions there are no oppositely oriented spins. Sure, absolutely. Yeah, clear. Yeah. Sure. So let's say here are just examples of the evolution of the fermion density at different KFA values. Fermion density meaning atoms remaining in the upper branch after a certain time. And at the meantime, I show the interaction shift renormalized to the initial interaction felt when we pumped up the atoms in the upper branch as a function of the whole time. And as you can see, for low KFA values, yeah, only small and slow variations of the two observables are revealed. That is consistent with, okay, I just start with a weakly interacting, weakly repulsive Fermi liquid. I go to a weakly repulsive Fermi liquid, nothing happens. But as KFA becomes on the order of 1 or larger, we observe that both observables undergo a fast and strong drop as a function of time. That we interpret as a concurrent development of pairing processes towards the lower branch and the development of anticorrelations in the upper branch. So first of all, we focused on the short time dynamics. And in order to do so, we just look at some time window that is within the first 200 microseconds from the end of the pump pulse in the strongly interacting regime. And in order to increase our temporal time resolution, we reduced the duration of the probe pulse down to times as short as 50 microseconds. Yeah? This enabled us to extract the rates for the pair formation and for, let's say, the sort of rate for I don't want to say ferromagnetic instability, but let's say something like this, yeah? Essentially, what we do is we just take these trends measured in the experiment, and then we fit to a linear trend like this, yeah? And we extract for different Ka values both gamma pair and gamma delta. And as you can see, both rates are kind of comparable. They are very, very fast because these are in units of 1 over the Fermi time. And what is kind of surprising and nice to see is that the rate for the buildup of anti-correlation in the repulsive Fermi liquid appear comparable but faster than the pairing ones. Yeah? And this is completely opposite to what theory by Demmler and collaborators of a few years ago expected based on some studies of the most unstable mode growth rates for both kind of instabilities. In turn, what we find, and this is something like a result completely compatible with what we observed already in the impurity limit, is that the pairing rate that we measure is fully consistent with three-body processes nicely fitted with Di Petros formula for 3 fermions recombining in vacuum. On the other hand, the extracted gamma delta values are almost quantitatively in agreement with the rate of the most unstable mode calculated by Pecker and Demmler back in 2011 for the Stoner instability. Yeah? And according to their theory, let's say the most unstable mode is something very similar to what Patricia was showing us last days. It is expected to develop initially at wave vectors on the order of kf over 2, and then correspondingly form very small domains of sizes of really very few interparticle spacings. And then, in the absence of pairing, as in the case for the weakly interacting Bose gases, domains would then have the possibility to grow larger and larger over longer and longer times. However, this is not what we see. And here I just show you, let's say, the leftover population in the upper branch as a function of the evolution time. For instance, here it's at KFA over 2. And as you can see, essentially, pairing strongly depletes the fermion density really in something like sub-millisecond timescales. Very, very rapidly, the repulsive Fermi liquid initially with all atoms in the upper branch become something like a mixture of dimers and that represent the majority component and leftover fermions on the order of only something like 20% at this KFA value. On the other hand, let's say we don't have any kind of indication of macroscopic spin demixing by looking at in situ images of the 2 spin clouds and as well of the molecules. So essentially, it looks like from these images that spin up, spin down, surviving fermions and the molecules that are created remain macroscopically overlapped at all times. And more sophisticated investigation of spin density fluctuations that would increase as domains would form over sizable length scales feature only a 2-fold maximum increase that is kind of consistent with the formation of domains of sizes on the order of a few kf to the -1, but on the other hand, we cannot exclude that the same thing could come from just heating. Okay, here it's gone heating. Great. On the other hand, if we look at the long-time dynamics as concerns the interaction shifts, what is kind of surprising to see is that also the interaction shift that dropped very, very quickly at the very beginning of the dynamics very rapidly goes down and it never comes back. I mean, it remains as essentially the surviving fermions, these 20% of fermion population left over very long times behave like non-interacting, although they are completely macroscopically superimposed to the Bose gas of pairs. And this is kind of just illustrated for different KF values. Here I just plot something like the average value of both observables sampled over times between something like 10 and 40 milliseconds after the pump pulse. And as you can see, the long time kind of steady population of the upper branch decreases as a function of the repulsive interaction strength. But on the other hand, also the interaction shift remains a very, very small fraction compared to the one that we measured in the paramagnetic state that we had initially. And what is important to notice is that these surviving fermions behave as non-interacting not only for what concerns the interaction shift, but also for what concerns the spectral width that is associated with kind of the coherence and of the atomic state. As you can see here, for instance, for KFA of order 1, here the width of our spectrum is initially relatively high due to collisional broadening of the spectral line, but very, very rapidly, and then kind of staying there forever, reaches a very small size that is essentially our Fourier limit of our probe pulse. And here I just show again this kind of width taken at long evolution times renormalized to the initial one observed for the palm pulse. So in conclusion, it seems that our data are absolutely inconsistent with the picture of a hot uncorrelated atom-molecule mixture. And if you want, this picture is ruled out simply by the fact that we observe very, very small interaction shifts that would not be consistent with, let's say, a paramagnetic state of atoms and dimers, simply because the atom-dimer interaction is essentially as repulsive as the atom-atom one. And also is inconsistent with the repulsive Fermi liquid at lower density, which means that although we cannot probe, as it was nicely possible for Patricia in the weakly interacting boson mixture, any kind of signature from the images of ferromagnetic domains or polarized domains, our data suggests that this long-time dynamics brings the system into a sort of emulsion state where, let's say, a minority of spin-up and spin-down surviving fermions remain in a highly correlated or anti-correlated state with within a bosonic bath. Yeah. So in conclusion, this work, I hope, convinced you that we could demonstrate that a repulsive Fermi liquid can survive as a well-defined quasi-particle, even for a balanced case and up to very strong coupling. At short time, we could observe, in contrast with theoretical expectations, that spin anti-correlation grow initially faster than the pairing ones. That is kind of interesting. And what is even more interesting is that the long-time dynamics suggest that both pairing and ferromagnetic correlation coexist in a highly non-trivial state that, to the best of my knowledge, no one observed before. What is also nice to stress is that our data and the picture that comes out from this experiment are kind of consistently explaining all observations coming from previous experiments, which is also nice. Just good, done. Just in the last minute, let me tell you very briefly about future possible plans we could do with this system. So one kind of measurement that we have not done so far regards possible transport and dynamics of both atoms and pairs created within this emulsion state. For sure, it would be extremely interesting to go to lower dimensions, so preparing one-dimensional or two-dimensional Fermi gases, because the ferromagnetic and pairing correlations and rates can change considerably. And also in weak optical lattices, it is expected, at least from the theory side, that ferromagnetism and ferromagnetic instability could take place easily, more easily than in the bulk. One thing that it seems probably a bit provocative, but it's also nice to think that this way of starting from the upper branch let the system relax to this mess, kind of, that however lives for a very long time, may enable you to dynamically access exotic superfluid phases that would be extremely challenging to observe if you would prepare the ground state. Yeah? And last but not least, I have absolutely no time to discuss about this, but we are also setting up an experiment that deals with the Fermi mixtures with kind of no pairing instability, and this is a chromium-53 lithium-6 Fermi mixture. And with this, I thank all the people of the Lithium Lab that contributed to this work that I told you about. Obviously, it was a very nice collaboration with Wolfgang, Theory, and people involved in the new setup that we are building in Florence. And I thank you for your attention.
Thank you very much. Questions? Start with Caden again.